For 33 episodes, we have mostly pictured a model as one solid block. Text goes in the top, flows down through every layer, and every single one of its parameters fires for every single word. That is called a dense model, and it has an uncomfortable law baked into it. If you want it smarter, you make it bigger, and if you make it bigger, every token gets more expensive because there is simply more network to run every time. For years, that was the tax you paid for scale. But many of the largest, most capable models you use today quietly broke that law. Inside them, the network is not one block at all. It is a whole committee of smaller subnetworks, and for each word, a tiny gatekeeper picks just a couple of them to actually do the work. This is mixture of experts, and it is how a model can be enormous and cheap to run at the same time. Quick note before we dig in. If you find this useful, subscribe and drop a topic you want explained in the comments. Now, let us get into it. Here is the whole idea in one sentence. Mixture of experts is an architecture where the model is split into many expert subnetworks, and a small router chooses only a few of them to run for each token. So the model can hold a huge number of parameters while only activating a small slice of them on any given step. The word that matters there is only. A dense model uses all of itself, all the time. A sparse mixture of experts model uses a little of itself on purpose. Let me show you the machinery because it is simpler than it sounds. Inside certain layers, instead of one big block, you place many parallel blocks called experts, maybe 8 of them, maybe hundreds. Then in front of them, you put one small, fast network called the router, or the gating network. For each incoming token, the router does one job. It scores the experts and picks the top few, the top K, to handle this particular token, and it ignores all the rest. Those chosen experts run, their outputs get blended, and the token moves on. The next token might get a completely different pair of experts. Nothing tells each expert to become the grammar expert or the Python expert, by the way. That specialization emerges on its own during training, as the router gradually learns to send similar tokens to the same places. Let me make it concrete with real models. Mixtral from the French lab Mistral has 8 experts in each of these layers and lets the router pick 2 per token. So at any moment, 6 of its 8 experts are sitting idle. DeepSeek-V3 pushes the idea much further. It uses hundreds of finer-grained experts and picks a handful for each token, and the payoff shows up in one stunning pair of numbers. The full model holds around 670 billion parameters, but for any single token, it only switches on about 37 billion of them. That is barely 5% of the model doing 100% of the work on every step. You get the knowledge capacity of a giant at the running cost of something a fraction of its size. Now here's the catch, and it takes us straight back to episode 9 because this is exactly where people get burned. Mixture of experts saves you compute, but it does not save you memory. Even though only that 37 billion parameters run on a given token, you never know in advance which experts the router will pick, and it changes token to token. So you must keep every single one of those 670 billion parameters loaded in memory, ready to go. Remember the rule from the VRAM episode. The whole model has to fit. So a mixture of experts model gives you the speed and cost of a small model per token, but it demands the VRAM of the enormous model it truly is. That is the real trade. You are not shrinking the model, you are only lighting up a piece of it at a time. So how does this land depending on who you are? As an individual, this is mostly invisible good news. When a frontier model feels both very smart and surprisingly fast, mixture of experts is often part of why, and some of the strong open models you can run locally are sparse. Letting a machine punch above the size it looks like it should handle, as long as you have the memory to hold it. As a startup renting a model through an API, you feel this purely as better economics, more capability per dollar, because the provider is only paying to run the active slice for each of your tokens. And as a large enterprise running open models in-house, this is where the trade gets sharp and deliberate, because you have to budget for the full parameter count in VRAM, the giant memory bill, even though your per-token compute behaves like something far smaller. It is a genuine capacity planning decision, not a free lunch. So let us bring it home. A dense model runs all of its parameters for every token, which makes scale expensive. Mixture of experts breaks that by splitting the network into many experts and letting a small router pick just the top few per token. So, models like Mixtral and DeepSeek-V3 can hold hundreds of billions of parameters while activating only a sliver, buying the compute cost of a small model with the memory cost of a huge one. That is one of the deepest tricks behind how today's biggest models stay fast. Now, we just spent this whole episode cutting down how much of the model runs. In the next one, we go after a different kind of waste, all the work a model repeats every single time it reads the same long prompt. We will recall the KV cache from our memory discussion and see how prompt caching turns that repeated work into something you compute once and reuse, cutting real cost and latency. That is where we go next. Content. That is the core of it. If this helped, hit like and subscribe, ring the bell for the next deep dive, and tell me in the comments what you want broken down next. Thanks for watching.